So we've been talking about the strength of association between two variables, but what about the strength of evidence? Is the difference between the groups statistically significant? So our null hypothesis will be that there's no association between the groups. So we're going back to that infant attachment study. So here it's going to be no association between the type of carrier and the type of attachment. Right? We're sort of assuming that what type of carrier the mother used didn't make a difference. So if we wanted to write this in terms of a parameter, we're going to let the parameter pi be the long-run probability of forming a secure attachment. So basically we're saying if there's no association, that the probability of a secure attachment in the soft group would be equal to the probability in the plastic group. Okay. The alternative for a chi-squared test is that there is an association between the variables. And chi-squared tests are always two-sided in the sense that it's always just going to be the parameter is not equal to the other one. So we've already talked about 3 statistics that you can use for categorical data. I'm going to give you one more. This one is called a chi-squared statistic. So chi-squared statistics work by looking at the difference between observed and expected counts. So observed counts, those are the counts that are there in your actual data. And the expected counts, that's what you would expect based on the null hypothesis. So what would you expect the counts to be if the null hypothesis were true? So let's try to find the expected count in this first box here. So the soft carrier and the secure attachment. So if there were really no association between the type of carrier and type of attachment, we would expect the same probability of attachment in each group. And what should that probability be? Really the best that we can do to estimate is to use the data that we already have. Right, so we can see overall in this data set, 29 out of 49, or about 59%, have secure attachments, right? And we would expect that 59% to be the same in both the soft and the plastic group. So if we did 59% of 23, right, so multiplying this fraction times 23, we would get 13.6 secure in the soft group. So I'm going to put that here. And it feels a little bit strange to have a decimal when you're talking about a number of babies, but when we say expected, we really mean what do we expect on average. So we do usually keep the decimal places there. So you can reason this out, but there's also a formula for deciding what the expected counts are. And you can see how it connects to what we've already done. So we're going to use these numbers, so 29 and 49 and 23. So we're going to take if we look at it, we've multiplied the row total, that was 29, times the column total, that was 23, and divided it by the overall total. So it's rearranged a little bit from the way we did it, but this is how you usually write the formula for the expected counts. You could do that for each of these boxes, or if you were feeling lazy, you could just subtract to get the expected counts in the other cells. So if we do 29 minus 13.6, we get 15.4. 23 minus 13.6 is 9.4, and 26 minus 15.4 is 10.6. So we only actually had to know one of these values, and we could just subtract to get the rest. So this is actually called having 1 degree of freedom, and we'll talk more about that in a little bit. All right, so let's use this to calculate the chi-square statistic. Okay, so for each cell in the table, I'm going to do the observed count. So for the first one, that would be 19. That's our actual count. Minus 13.6 is the expected count. Do that squared, divided by 13.6. And then notice the sigma, that's a sum. So I'm going to just do the same thing for each cell in the table. And I won't really have you do this on a test. We'll have R do it for us, but it's still good to know what the formula is doing. And when I do that, I end up with a chi-squared statistic of 9.846. So let's think about what it would mean to have a chi-square statistic that was large, right? If you have a large chi-square, that means you have a big difference between your observed and your expected counts. In other words, your actual data is really different from what the null hypothesis told you to expect, right? So if you have a large chi-square, that means that you have strong evidence against your null hypothesis. But by now we know the question. When we say a large chi-squared is strong evidence, how large does it need to be to convince us, right? We need something to compare it to. So we can do this with theory, or we can do it with a simulation. So let's start with a simulation just to kind of get the logic down. Okay, so how would you design your simulation? I have it side by side next to the odor ratings example. This was just comparing two means. How could you modify that to make it work for a categorical response? So pause the video, see if you can come up with a design for the simulation, and also answer the other questions on the right side of this slide. So the main modification here comes from the fact that we have a categorical response variable instead of a quantitative one. So usually we would be writing quantitative values on our cards. Here we could just be writing secure or insecure, or we could even just use different colors if we didn't want to write it. So let's use 29 blue cards. I'm going to do that to be consistent with the applet. 29 blue cards, that's going to represent a secure attachment, and 20 green cards to represent an insecure attachment. So just like before, we're representing the response variable, and we're assuming basically that the response was going to be what it was going to be, right? Some babies were going to be secure and some insecure, and that the type of carrier actually had nothing to do with it. Okay, so we shuffle all the cards together, and we haven't labeled them as soft or plastic carriers. We're just shuffling everything together because as we're doing that, we're assuming that the carrier makes no difference. Okay, so we shuffle everything together, and then we want to mimic the random assignment. So we're going to deal into groups that match the sample sizes that we have up here. So groups of size 23 for the soft group, and 26 for the plastic group. And we need something to summarize this simulated sample. And because we've used a chi-squared test as our statistic, we'll use a chi-squared test here. Calculate chi-square and repeat. So the last question on the slide asks you to make a decision based on this graph. So this graph is showing you the values of chi-squared that you would expect to get, assuming that the null hypothesis is true, right? So in this case, assuming that there's really no association. Okay, so we would find our statistic down here, maybe there, 9.846, and we would see how likely is it to get that value or something more extreme. So already I can tell it looks like it would be pretty unlikely. I'm going to use an applet to calculate this value. So on the ISI applet page, we're going to go to Analyzing Two-Way Tables. And since this is 2 by 2 data, we'll put it in here. So we had in the soft group 19 successes and 4 failures. And in the plastic group 10 successes and 16 failures. Okay, so we can see we've got our bar graph here that matches our data. And we've got our statistics. Notice there's an option, the ones that we've talked about, difference of proportions, relative risk, odd ratio, a few more we haven't talked about. But we're going to use chi-square here. And we do the shuffle options. I'll show it because it's kind of satisfying. Shuffles the cards together. And for that particular shuffle, it records the chi-square statistic. Okay, so we can do a whole bunch of these. That went pretty fast. Maybe I'll go ahead and do 9,000 more. Okay, so I've got my chi-squared distribution, and I'm going to find our statistic, 9.846, and count how often we get that chi-square statistic or something even more extreme. So you can see it was rare, 31 out of 10,000 times that this happened. So that's our p-value, 31 out of 10,000, or 0.0031. And that's telling us that this would be unlikely just by chance, right? It would be unlikely to get our chi-square statistic, chi-square equals 9.846 or greater. It would be unlikely to get that chi-square statistic or greater, assuming that the null were true. So assuming that there were really no association between type of carrier and type of attachment. So it would be very unlikely to get this kind of result just by chance. So if this is unlikely to occur by chance, then our conclusion is that we have strong evidence of an association. So something I wanted to point out is that it doesn't actually matter which statistic you choose. So like, let's say we had picked a difference of proportions. If we look at this, obviously this graph looks very different. It's centered around 0 instead of being skewed like the chi-square distribution was. And we can find 0.441, and we're going to do a two-sided test to be consistent. But notice we get the same p-value that we got from when we use the chi-square statistic. What about if we use a relative risk? So the shape of the graph has changed again, and I'm going to do 2.148. And it's counting, notice that it's not symmetric anymore because a ratio of 2.148 is actually the same relative risk as 1 over 2.148. So that's how we count it when we look beyond, but again, the p-value comes out the same way. So there's multiple options for doing a simulation-based test, but the benefit of a chi-squared statistic is that it allows you to do a theory-based test. So I can overlay my chi-squared distribution to sort of get a sense of what would happen without actually doing the simulation. So just like the F and the T distribution, there's different versions of this distribution depending on what your degrees of freedom is. So 1 degree of freedom will look like what we saw on the applet, where we have this vertical asymptote at 0, and then it gets flatter and flatter as it goes out. Whereas if you had, say, degrees of freedom 4, you're going to have this hump on the left side, still skewed right. And as your degrees of freedom gets bigger, it would actually get more symmetrical. All right, so how you calculate the degrees of freedom is you're going to look at the number of rows minus 1 times the number of columns minus 1. So in this case, we're not going to count the totals. So the number of rows that we have is 2, and the number of columns that we have is 2. So we do 2 minus 1 times 2 minus 1, and we have just 1 degree of freedom. And we talked about how that means that you end up only really needing 1 value in the table, and you can figure the rest of it out just by subtracting from the totals. Okay, so that's how you decide which chi-squared distribution to use, but that's only appropriate if your validity conditions are met. So the validity conditions are that your expected counts need to be at least 10 for every cell in the table. And in this case, that's actually not quite met because we had 1 cell in the table where the expected count was only 9.4. So 9.4 is actually a little bit less than 10. So we would use a simulation-based approach instead of a theory-based approach. That would probably be a little bit safer here. So when your validity conditions aren't met, you should use a simulation-based approach instead of theory. And if we try it in the applet, we can see we actually do get a pretty big discrepancy between our simulation-based p-value and our theory-based p-value. So in this case, they would probably lead to the same conclusion, but that's a pretty substantial difference in p-values.